Welcome back to ValueVest Daily. As a reminder, the following analysis is for educational purposes only and does not constitute financial or tax advice. Let's run a stress test. The date is March 2nd, 2026. A localized geopolitical disruption halts all operations at QatarEnergy's massive Laffan industrial complex. The global impact of this single event is immediate. Within hours, roughly 30 to 38% of the planet's total supply of semiconductor-grade helium disappears. The financial contagion spreads rapidly. Tier 1 semiconductor fabricators in South Korea, facilities reliant on these exact exports, are forced into strict rationing protocols. Spot prices for the gas spike by 35 to 50% in a matter of days. We are looking at a hard physical limit on the artificial intelligence sector. The primary bottleneck for scaling these networks is no longer software engineering or algorithmic logic. The AI industry has entered the scarcity stage. The deployment pace and ultimate valuation of trillion-dollar computing networks are directly governed by the availability of invisible, physical commodities. During the 2010s, the investment landscape heavily rewarded scalable code and digital intellectual property. Today, the market relies on the mass manufacturing of physical hardware, like GPUs, or graphics processing units, which are the specialized chips required to run AI models. This chart illustrates the shifting constraints on technology over time. We see the progression from code and logic in the 2010s to compute and GPUs in the early 2020s. The actual choke point has moved further down the supply chain, past the silicon chips themselves, into the thermodynamic commodities, the raw atoms and molecules required to manufacture that hardware. Helium represents the foundation of this transition, functioning as a strict industrial requirement for every advanced semiconductor node. Projected exponential growth models for global data center buildouts require a corresponding exponential increase in hardware. Without securing these foundational elemental resources, those growth models are mathematically impossible to execute. Let's look inside a modern semiconductor fabrication plant. This is a multi-billion-dollar vibration-free environment filled with highly automated tools. These facilities operate 24 hours a day, 7 days a week. They demand a flawless, uninterrupted flow of ultra-pure resources to function. The financial penalties for supply interruptions are severe. A single drop in gas pressure or purity can ruin an entire production batch, resulting in millions of dollars per hour in scrapped materials. The manufacturing process requires microscopic precision to successfully print billions of individual transistors onto the surface of a single silicon disk. Protecting this fragile, high-value wafer from self-destruction during the volatile manufacturing process is the single greatest engineering challenge in modern computing. This is plasma etching. It is the process of using superheated plasma to violently carve nanometer-scale pathways into the silicon. This intense reaction naturally generates extreme, destructive heat. Inside the vacuum chamber, the mechanical setup looks like this diagram. The flat silicon wafer rests directly on top of a specialized pedestal called an electrostatic chuck, which acts as a clamp holding the disk securely in place. At the microscopic level, the interface between the wafer and the chuck is uneven. This creates a tiny, irregular void where that devastating heat gets trapped during the etching process. To solve this, helium gas is pumped directly into this microscopic gap between the wafer and the chuck to act as a thermal bridge. Helium is uniquely suited for this role due to two first-principle physics properties. It possesses the highest thermal conductivity of any non-explosive gas, and it remains a fluid even at extreme cryogenic temperatures. These specific properties allow the helium to instantly and uniformly whisk the plasma-generated heat away from the silicon base. This specific heat transfer mechanism prevents the wafer from warping under the thermal load. Alternative gases simply cannot perform this function. Nitrogen or argon mathematically fail to transfer heat fast enough to protect architectures built at 3 nanometer or 2 nanometer scales, a nanometer being 1 billionth of a meter. For the advanced computing nodes powering the entire AI sector, helium is thermodynamically irreplaceable. The geological reality of helium extraction presents a severe constraint. It cannot be synthesized efficiently in a laboratory. It is strictly recovered as a byproduct of natural gas extraction. This chart displays the extreme geographic concentration of the global helium supply. The United States holds roughly 40% of total reserves, while Qatar holds roughly 19%. with Algeria and Russia making up smaller fractions. Returning to our March 2026 disruption scenario, pulling Qatar's 19% out of the global market creates an immediate gaping deficit. Despite their massive capital resources, semiconductor fabs face a severe structural weakness. The facilities physically cannot store more than 1 to 3 months of helium inventory on site. Once those local reserves run dry, the downstream economic contagion begins with delayed manufacturing shipments of next-generation AI GPUs. That initial bottleneck triggers secondary economic impacts across the board. The constraint forces inevitable price increases for consumer electronics and electric vehicles. A localized pipeline or facility issue in the Middle East cascades mathematically into stalled multi-billion-dollar data center deployments worldwide. Tier 1 manufacturers are attempting to mitigate this supply chain threat through massive new CapEx, or capital expenditure, which refers to funds used to acquire, upgrade, and maintain physical assets. The specific engineering solution is detailed in this diagram. Fabs are retrofitting exhaust networks with closed-loop recycling systems designed to capture escaping gas, purify it, and return up to 95% of it back to the start of the process. These systems introduce severe economic friction. They require immense upfront capital and are incredibly difficult to retrofit into older, legacy fabrication plants. We are also seeing a geographic supply response. There is a strategic push to bring new domestic extraction projects online in structurally secure regions like the United States and Canada. Recycling and domestic extraction offer long-term stability. However, the transition period leaves the immediate AI hardware boom dangerously exposed to geopolitical friction. The overarching lesson of this stress test is clear. Exponential digital growth is strictly bound by finite physical realities, specifically energy, water, neon, and irreplaceable gases. Properly valuing the technology sector over the next decade requires understanding these invisible infrastructure bottlenecks before the wider market reacts to them. If you want to spot these constraints early, subscribe, like, and share ValueVest Daily for daily learning opportunities before deploying your capital. Leave a comment below specifying which high-risk, high-reward market sectors you want us to stress test and analyze next. True market edge requires prioritizing the physical atoms that enable the algorithms.